Hey, my name is Radek. I'm a senior data scientist at NVIDIA. And to help you get up and running quickly with this competition, I prepared this notebook and this short video walkthrough. It is extremely vital that you get started as quickly as you can because this competition will last for only 7 days. So I'm hoping that what I have prepared for you here will be of help. To give you an overview of the competition, we will be once again working with synthetic data. So the organizers, Kaggle, trained a deep learning model on the original data set. It is the IBM HR Analytics Employee Attrition and Performance dataset. It's available on Kaggle, so you can take a look at it if you'd like. But the idea is that a deep learning model was trained on this dataset, and now it's being used to generate the dataset for us to play around here with in this competition. So we can assume that the relationships will be similar between variables as in the original dataset, but they will not be exactly the same. What columns, what variables do we have here? Well, we have 33 variables describing an employee. So in the dataset for each row will be a single employee, and based on the information contained in that role, we are to predict whether the employee will attrit, whether they will quit or not. Okay, so the metric that has been chosen by the organizer here is the area under the ROC curve, which makes a lot of sense because this is a binary classification problem, right? We are predicting yes or no, whether the employee attrits or not. That is probably a good choice of a metric. We begin by loading in the data, looking at the data here really quickly. So we see the variables that have been provided to us. Now, the initial problem that jumps out is that certain variables are string variables. And our model that we will construct, it will be a light GBM classifier, right? It can deal with variables, with categorical variables, but only once they have been encoded to integers. So this is something that we will have to do here as part of the preprocessing. Now, every gradient tree boosted model can deal with categories encoded as integers. So that's an obvious thing. But with light GBM, we actually can specify which are our categorical columns, and then there is a bit of extra functionality that light GBM provides, which can improve the scores, and it actually does here. All right, but let's take a look at the data. So we have 1600 rows for our train set. We have 1100 rows for our test set. So the data is quite small as compared to how many features we have. That means that we will have to be extremely cautious to not overfit, and that definitely can be a challenge in this competition. Now, do we have any NA values, any missing values? No, there are no missing values, so that's nice. This part of the preprocessing we can skip. And let's see. So we begin by training our first model, and it will be a light GBM classifier. Now, in the previous in the first episode of the Playground series that Kaggle launched this year, a very interesting observation was made. If to the synthetic data we add the original data that the model was trained on, the score improves. And that makes sense. We're training on more data, and possibly, some of the relationships between variables can be a little bit more clear or pronounced in the original data. That can be, some of the relationships can be lost in the generative process in which the synthetic data is created. But here, that is an interesting question. will adding the original data help our model? And here's where I'm adding the original data. I'm creating a source column. So that's another thing that was observed in the previous competition. If we give our model the information on what data it is seeing for each row, whether it comes from the original data set or from the generated data set, this further improves the score. So I added this piece of information for our model here as well. And let's see, well, I ran this notebook a couple of times already, and just by adding this original data, our score improves dramatically from 0.88 to 0.92. That's a dramatic improvement. And why is that? Well, most likely because we start with very, very little trained data, right? So if we grow our trained data essentially, twice, right? If we grow it by 100%, then we can expect better results. And this is what we are seeing here. So adding the original data is definitely helpful. Now here, we're just picking the features for our model to train on. We're saying that no, we don't want to train on the ID column. It's just a it's a column that doesn't overlap between train and test, and it's just a column introduced for organizational reasons, I would imagine. Now the attrition, that's the target, so we remove it from our train features. And last but not least, we mark our target, that is attrition. That is the column that we will be hoping to predict. So as mentioned earlier, some of our columns, and exactly these columns right here, they are categorical columns represented as strings. So the levels are represented as strings. And in order for our LightGBM model to work with these categorical columns, we have to encode them as integers. That's what this piece of code I looked up on Stack Overflow is doing. Now, it's okay to do so for this data set, but you have to be very cautious when you use this functionality on other data sets because you can introduce leakage, and also you can essentially on other data sets you might have to deal with missing data and so forth, where certain columns that have certain values in the train set, they have different values in the validation set. So just in general, a word of warning, we are okay to use this functionality for this problem, but if you're working with a different data set, then maybe this is not a great solution. However, this does the job for us quickly here and well. So I'm selecting the 8 columns, or sorry, 9 columns, because the source column that we introduced, it also has levels represented as strings. So we will be encoding these 9 columns as integers. And this is what we are doing right here in this cell, right? So I'm first transforming the train set, then transforming the test set. And we move on to training our classifiers. So we will be using a stratified k-fold splitting strategy. We will split our train data set into 10 folds for training and for validation. Now, the interesting bit here is that the data set is unbalanced. So we have roughly, from what I recall, 5% of positive targets, and the rest are negative targets. And that is another consideration that we might want to address somehow in our training scheme. Here I'm addressing this to some extent by saying, hey, let's use stratified k-fold instead of just regular k-fold, because as you see here, we are stratifying the splits on the target variable. So given how poorly represented the positive class is, I want roughly each fold to get the same number of positive examples. All right, so we're training the classifier, and there are certain values here that essentially this number of estimators that I picked based on very short and very, I would say, even primitive hyperparameter search. I essentially just ran this a couple of times, seeing which number of estimators would give the best mean score across all folds. But definitely a more elaborate hyperparameter tuning strategy can be leveraged here, and it should lead to an improved score. And what I mentioned earlier, the functionality in LightGBM that allows you to, that deals with categorical features, it splits on them, LightGBM splits on them in a more elaborate and interesting way than it does with numerical values. So I'm specifying the categorical features here, I'm specifying the metric, and we're off to the races. We train our classifier, we predict the probabilities, and that's so that our predictions can play nicely with the ROC area under the curve score. I'm selecting the predictions for the positive class because the predict proba returns an array that is of size of the length of the data set with two columns. So in the first column we have the probability of a given example representing the negative class, so being having the attrition value of 0, where the positive class is in the second column. And these values on a per row basis should sum up to 1. However, this is just how scikit-learn does it, so why not? Let's play along with that here, and let's move on to what we have next here. So here we're looking at feature importances, and this is a super useful thing to do when starting to play with a data set, when you want to understand, when you want to start diving deeper into your data set and understand maybe where to focus your initial attention on. So instead of creating a lot of plots and looking at correlation coefficients, instead of going through that process manually, let's query our model and let's ask it, hey, which of these variables do you find to be the most relevant to the predictions, to carry the most signal? Right, so this is not an exhaustive inquiry. The model will not tell us everything there is to know about the data set, and many relationships that can be crucial to achieving a very good score can be missing, because gradient boosted tree models out of the box, they don't address interactions to a great extent. But still, this is a starting point, and here especially we have only 7 days. Maybe instead of looking at performance rating or education level, maybe we should look at variables and study those, like the monthly income, like daily rate, like monthly rate, etc. Now, I find it very interesting that the performance rating is not useful at all for predicting employee attrition, and I'm not surprised. Based on my corporate experience, performance rating is is an interesting ritual that you go through in a corporation. Let me park it there, and I'm sure it has a lot of merits. Yes. But let's go back to this notebook at hand and focus on data science instead of some tangential musings. Since here we will be assembling our predictions from the 10 classifiers that we trained here, LightGBM classifiers, why not take it a step further? Why not also add CADBoost classifiers to the mix? Just to test the water how ensembling might play out. And we see that Here CADBoost gets a much better score than our LightGBM. That is possibly because we haven't tuned our LightGBM model, and CADBoost is it's its feature that without parameter tuning it can still perform extremely well. Sometimes it is, or not sometimes, but often it is at a cost of more computation and longer run times. But you know, if we can get such an improvement in the score for essentially essentially free, essentially just some extra compute, I'm all for this all day, every day. So let's take a look at what's happening here. Right, we're making a submission and we're predicting using classifiers that we have in our classifiers list, and there are 20 of them. There are 10 LightGBM classifiers and there are 10 CADBoost classifiers. So we are generating predictions. We are then combining the predictions into a single array, and we are taking a mean of them. And finally, we are pulling it all together into a submission file that we save to the disk, and we're ready to make a submission. Now listen, if you found this walkthrough useful, if you find this work that I'm doing here useful, please upvote the notebook. This can go a very long way in allowing me to prepare such material for you going forward. I really appreciate your help. Thank you so much for listening, and have a lot of fun and all the best to you in the competition. I'm hoping that we will learn a lot together by participating. Thank you so much. Bye bye.